Okay, so hello to everybody, and hope everybody's doing as well as possible given the times. I'm going to talk about absolute earthquake location of the 2019 Ridgecrest, California seismicity, and talk about two or three main interesting points. In particular, I'd like to mainly discuss, did the magnitude 7.1 main shock rupture in this sequence require incitation by the large foreshock, an Mw6.4 earthquake. I also note the number of people I talked to while working on this, and have thanks to them. So what I'm showing I call calibrated absolute location of earthquakes. First, I'd like to point out that absolute earthquake location forms a foundation and framework for many parts of seismology, earthquake response, basic seismological studies, and advanced seismological studies, including relative earthquake location. Relative earthquake location requires an absolute earthquake location foundation. Here I will show calibrated absolute relocation for Ridgecrest using a number of 1D and 3D velocity models, probabilistic global search location algorithm, which is important because it's robust to model errors and arrival time errors in the data, and also be using what are called station corrections to improve the locations. So the setting is Southern California, the spectacular desert area. The map here shows Los Angeles and the area of the Ridgecrest earthquakes. They were in July 2019. There was a magnitude 6.4 earthquake, followed, I think it was 34 hours later, by the large main shock of magnitude 7.1, one of the largest earthquakes in California in the past 20 years. The black dots here show the stations used for the study. And then the gray box here, or on the right, this shows the study area. And what I'll be showing is the relocated seismicity from just before the magnitude 6.4 earthquake until several days after the magnitude 7.1 main shock. And most of the slides I show, they have colored seismicity, which is the earthquakes between the magnitude 6.4 earthquake and the magnitude 7.1 main shock. And then the dark gray dots on this plot are aftershocks of the magnitude 7.1 earthquake, also defining the faults that were ruptured. Start with a movie where you can see the 3D setting of the earthquake and the relocated seismicity. I think, like very many aftershock sequences, if not all, it's a very 3D problem, and if there's not good visualization in 3D, it's very hard to understand what's going on, and also you can get misleading interpretations if you just look at 2D sections. So here you notice which direction is north, which is flying around. The scale of the study area, this is 10 kilometers. Can you see the cursor as I move it?
Yes, we can see your cursor.
Okay. And then again, in color are the earthquakes between the magnitude 6.4 and magnitude 7.1 main shock. And the surfaces here, the polygons, are my interpretations of faulting structures, main faulting structures between the magnitude 6.4 and magnitude 7.1 main shock. And then again, the gray dots are the aftershocks after the magnitude 7.1 earthquake occurred. So I start with looking at depth sections, view from the southwest of the sequence, depth sections. And here I'm comparing 5 different models I used, 3 1D models and 2 3D models, and showing the seismicity and depth to show the differences. There are some significant differences in depth of seismicity, clustering, the blurriness of the seismicity. But in particular, the depth range of the seismicity changes somewhat with the different velocity models. And a particular interest is the range at the top near the surface, the depth range where there is very little seismicity, that changes somewhat. On the bottom left, I show the preferred 3D model. It's a 3D model that was developed through tomography for the Ridgecrest area. And most of what I show, I think everything I show later, are locations in this preferred 3D model. Also on the lower right, I show the same depth section with the catalog locations, the USGS and Southern California Seismic Network obtained. This is what you find on the internet if you look at the USGS website of the seismicity for the Ridgecrest sequence, and some more precise template matching and relative location seismicity from Ross et al. 2019. So there's the difference in depth of seismicity, and there's other things that show up. In particular, when you have 1D models with layer cake sharp boundaries, you often get artifacts from the layers, these horizontal streaks of seismicity, which also show up in the USGS catalog. And notice also that the Ross et al. Seismicity has earthquakes a bit more scattered than some of the locations I'll show, but that's also partly because they have more events because they did the template matching. But they do have seismicity up to quite near the surface. And also the USGS catalog has seismicity right up to the surface. So the same view, but just showing the preferred locations in the 3D model. And the seismicity falls mainly from 3 to 12 kilometer depth. So there's about 3 kilometers near the surface where there's little or no seismicity. And the seismicity that is here could be primarily mislocated events, certainly some of the ones above the surface. This is not unusual, certainly in California and probably other places in the world, for strike-slip faulting. Here is a cross-section in the Parkfield segment of the San Andreas Fault. And in the colored part, I show that there is a zone of something like 3-4 kilometers near the surface with little seismicity, and then a zone of seismicity that's roughly the same depth range as we find for Ridgecrest. Off to the left here, this is the creeping section of the San Andreas Fault, so it's not quite relevant to the argument. Another interesting thing, or another problem with the data for this sequence, is that the main shock, magnitude 7.1, occurred a few seconds after a small aftershock of the magnitude 6.4 earthquake. And so the seismograms are overlapping. And it was difficult to get a depth for this earthquake. The USGS website still lists 8 kilometers of depth for this earthquake. I looked at the seismograms from the nearest stations, and I repicked them. And basically what I found is that the first arrival, which would be picked by an automatic picker, corresponds to a small aftershock of the magnitude 6.4 event. And the picks that correspond to the magnitude 7.1 main shock are secondary picks, shown here in red. And it's pretty certain that this is the main shock first arrivals, because they work very well in locating when you combine them with more distant stations, which do not see the signal from the small foreshock. So looking again at the same section we looked at before, but showing these the small aftershock main shock relocation plus the relocation of the magnitude 6.4 earthquake, we find the small main shock in green here, small aftershock that overlaps with the main shock seismograms here, and it locates well within the magnitude 6.4 aftershock zone. So there's pretty high confidence that that's a small aftershock for the magnitude 6.4 event. The magnitude 6.4 event locates at about 12 kilometers deep, which is also what everybody, the USGS and other relocations obtained. But the magnitude 7.1 main shock hypocenter locates very shallow at 4 kilometers, which is, as I said, is not the case in the USGS catalog, though some other relocation studies have shallow depth for the, also have shallow depth for the magnitude 7.1 main shock hypocenter. So now I'm going to go through the sequence between the magnitude 6.4 earthquake and the magnitude 7.1 main shock, showing some 3D views, though I'm going to turn the view a bit, and we're looking from the southwest, just like in the sections we showed. And I'll be discussing the seismicity and the faulting structures. And also, you may be interested to know, this is the mapped surface ruptures from the sequence, are the black lines. And that gives you an idea of where the surface is, but also where there was surface faulting or cracking and ruptures. And one of the main points here is to define that the magnitude 6.4 earthquake had a duplex structure with 2 levels of faulting, of orthogonal faulting. So for a couple hours before the magnitude 6.4, there were small foreshocks up to magnitude 4, immediately in the region or very close to the magnitude 6.4 hypocenter. So there was a small foreshock sequence, several hours, and basically at the hypocenter or very close to the magnitude 6.4 hypocenter. There's the magnitude 6.4 hypocenter earthquake. And this is the seismicity in the first 6 hours after the magnitude 6.4. So there's a scale at the bottom, and we're moving through the colored seismicity. And so this is the first 6 hours after the magnitude 6.4 to try and say what might be the faulting structures that ruptured immediately during the magnitude 6.4 earthquake. So the first faulting structure identified is a northwest trending structure that passes through the hypocenter, and it's a relatively deep structure. But there's a second planar structure, which is shallower and has an orthogonal southwest trend. And this little black spot, if you can see it, that shows the overlap between the two. So there's very little overlap. And then the shallower structure at the surface projection, because again, there's very little seismicity just near the surface. The surface projection of the shallower structure does correspond to many of the mapped surface ruptures. Not the case for the surface projection of the deeper structure, but if this truly is a deeper structure that's being defined by the seismicity, that's not unexpected. In this time, there's also a smaller crossing orthogonal structure at the north end of the northwest end of the seismicity immediately after the magnitude 6.4 earthquake. If we move a little further in time, another 12 hours, the seismicity migrates to the northwest. There's also some migration and seismicity around the faulting structures we've already identified. But there's migration of seismicity towards the northwest, which is where the magnitude 7.1 hypocenter will be. And also we see there's small clusters of events occurring in the first 5-10 hours after the magnitude 6.4 event. Again, in the immediate vicinity of the magnitude 7.1, future magnitude 7.1 hypocenter. A little further in time, a second perpendicular structure seems to be illuminated, and that was also activated by a magnitude 5.4 aftershock of the magnitude 6.4 event. And then we go to just before the magnitude 7.1 main shock, and there are more small clusters of events. These events occur in pulses, as you can see with the different colors. And again, they're very close to the magnitude 7.1, future magnitude 7.1 hypocenter. There's also, interesting, there's a couple more little clusters further to the north along what will be the future rupture plane of the magnitude 7.1 earthquake. And then the magnitude 7.1 earthquake occurs, and the aftershocks and other information, this earthquake illuminates a 55-kilometer long southeast northwest set of somewhat complicated set of faults with right lateral strike slip and some perpendicular structures. I try to indicate one here. It's a deeper perpendicular structure parallel to the crossing structure from the magnitude 6.4 earthquake. This is an attempt to show the same information as distance between the magnitude 6.4 earthquake and towards the magnitude 7.1 earthquake. So distance to the northwest from the magnitude 6.4 earthquake, and time relative to the magnitude 7.1 epicenter, hypocenter, origin time of the magnitude 7.1 earthquake. It's about 34 hours. This basically shows that these the crossing structures we identified. So the first crossing structure, which was associated with the magnitude 6.4 main shock, or just immediately after. The second crossing structure, 10 or 15 hours later. And then the magnitude 7.1 hypocenter. If we consider those three zones, we get an apparent migration of seismicity possibly with a sort of velocity of 160 meters per hour. But more importantly, this plot shows clearly these clusters of pulsing clusters of seismicity near the magnitude 7.1 hypocenter. So the first cluster is 5 to 10 hours after the magnitude 6.4 event. There's another sort of cluster pulsing another 10 hours later or so, 15 hours later. And there's a cluster or pulsing a few hours before the magnitude 7.1 main shock. So what is all this this seismicity, the time, the temporal variations, spatial variations, the faulting structures? What does this suggest about this earthquake sequence, and in particular the activation of the magnitude 7.1 main shock? Well, it seems that very likely that the magnitude 7.1 rupture, the very beginning initiation of this rupture, was probably an event in one of the events in these pulsating clusters, which grew into a large earthquake. And then the growth of this rupture, this initiation into a larger earthquake, how could this happen at a shallow depth where in general it's not thought that large earthquake ruptures initiate in strike slip systems, or in California in particular? So we have the magnitude 6.4 earthquake and identified faulting. So the idea is that the magnitude 6.4 rupture and its aftershocks with the migration increased the stress around the magnitude 7.1 hypocenter and helped the growth of this large magnitude 7.1 earthquake at shallow depth. So this is basically an argument much like Coulomb stress discussion, where we look at how much did a previous earthquake increase the shear stress and decrease the normal stress somewhere where a future earthquake might occur. And so in this case, from other studies, though not using the same faulting structures that I'm showing in this talk, but other studies have shown that the area of the magnitude 7.1 hypocenter has increased Coulomb stress from the magnitude 6.4 activity. So I would say that the magnitude 6.4 rupture, the main magnitude 6.4 rupture on the two faulting surfaces, plus the migration of aftershocks and activity towards the northwest, all of that created, in terms of Coulomb stress, a situation where the magnitude 7.1 rupture growth was highly favored. So that meant the magnitude 7.1, once initiated by these clusters of events, one of these clusters of events, small events, could relatively easily grow into a very large earthquake. So to put this in the context of what's understood about faulting in continental shear zones, in continental strike slip earthquake case, I again have the cross section I've been showing from the southwest, the magnitude 6.4 hypocenter, the magnitude 7.1 hypocenter, and then color the seismicity between the two earthquakes. So the magnitude 6.4 event is initiated, hypocenter is at 12 kilometers depth. And this is a depth where it's expected that spontaneous large event nucleation and growth is possible and is often seen. And it fits ideas of fault mechanics and seismic behavior in the crust, for example, from Schultz. However, the magnitude 7.1, as I've already mentioned, we've determined a very shallow hypocenter for this event. And so it's in an area where the spontaneous growth of large earthquakes is not considered likely. That is, if there had been no significant foreshocks, we would not really have expected a magnitude 7.1 earthquake to have initiated at this depth. What the sequence seems to show is that there was certainly much stored tectonic strain energy in the so-called seismogenic layer. And that was released in the magnitude 7.1 earthquake. So this means that in order to have the magnitude 7.1, there had to be initiation of rupture. But in this case, because the rupture was shallow, we would say that the magnitude 7.1 nucleation and growth required incitation by the magnitude 6.4 event. And by incitation, I mean the magnitude 6.4 event created the stress changes that allowed the magnitude 7.1 to grow, and also created stress changes and perhaps the pulsing clusters of earthquakes that we observed near the magnitude 7.1 hypocenter. The magnitude 6.4 also created the stress situation where these small earthquakes in the area of the future hypocenter would start occurring. If the magnitude 6.4 event had not occurred, then the magnitude 7.1 like rupture, the large rupture, might not have occurred until long in the future. This may have occurred through incitation by some other deep magnitude 6.4 like event, or perhaps with nucleation at greater depth somewhere along the magnitude 7.1 rupture. So no large foreshock, but nucleation and immediate rupture of the magnitude 7.1. Or perhaps even the rupture might have occurred on some nearby fault, 5-10 kilometers away. And this may have relieved the tectonic strain energy that had built up, that in fact was released in the magnitude 7.1 Ridgecrest earthquake that occurred. So these possible scenarios greatly complicate hazard assessment because they imply that the occurrence of some large earthquakes doesn't just depend on the properties of rupture zones that we may be able to estimate or image. It doesn't depend on the state of stress that we know sometimes in some ways, but we never know the absolute stress. And it doesn't just depend on the nearness to the end of some seismic cycle kind of concept. But the occurrence of some large earthquakes then also depends on having the incitement of a nearby, deeper, and perhaps smaller event. So in conclusion, I've shown a robust absolute earthquake location for the Ridgecrest sequence and defined faulting structures and shown the evolution of seismicity. The magnitude 6.4 event ruptured 2 non-intersecting orthogonal duplex structures, and the magnitude 7.1 hypocenter we've seen is unusually shallow. And then we discussed that this situation may have meant that the magnitude 7.1 nucleation and growth into a large earthquake may have required incitation by the magnitude 6.4 event. And this greatly complicates hazard assessment. I have a little more information at this link here, and I will post this talk also at this link, hopefully later today. Thanks very much.